Okay, here's a problem that involves straight conservation of energy. In this particular problem, there's a very heavy mass here, which is distance A above the spring. And so what's going to happen is this big heavy mass is going to be released. It's going to fall straight down and hit the spring, and it's going to compress it over here by so much distance. It's going to compress the spring by so much distance before it eventually stops. That's what springs do. They're allowed to stop things like that. And what we'd like to know then is what spring constant must this spring have if it was able to stop this heavy mass here in some distance, and I'll sort of outline the distance right here. I'll just call it delta S for, say, the spring compression distance right there. So if this before and after distance ends up being delta S, what must the spring constant be? Now your problem likely has a bunch of numbers in it and so on, but I'll just sort of hit the salient features here and you can worry about plugging in the exact numbers on your own. So it looks like to me it's a straight conservation of energy problem. In particular, I'm just going to say that E initial is equal to E final. That'll be a good guide through the problem here. And this is the sort of the initial configuration over here, where you see this mass high above the ground here, sitting above the spring. And in the final configuration over here, we see the mass all bunched up against the spring like that. So a couple things I should probably label in there. We definitely have this distance A above the surface of the spring here, isn't the surface of the ground. So I'll just say that additionally, perhaps something like this, that the mass ends up being a total distance h above the ground, say. That'll be the important parameter for potential energy. And when the spring is over here, when the box is over here compressed up against the spring, there'll be another distance in here. Let me just call it h1 or something like that, which is the height of the box above the ground when it's at rest. So it still has a little gravitational potential energy over here as well. So what we'll do now is just fill in our conservation of energy equation and see what we can get out of this. So the initial energies I see over here is this mass, the distance h above the ground. So I'll just go ahead and put an mg times a capital H in here. That's the potential energy of the mass before it's released. There's no potential energy stored in the spring because it's sitting here at its equilibrium position. In fact, there's no other energies in the problem initially. In the final case over here, what I see over here is I see a compressed spring storing some energy 1/2 k times delta S squared, because the spring is all bunched up, and 1/2 k delta S squared is the potential energy of a spring. And additionally, the box isn't quite all the way on the ground. It has a little bit more potential energy here, so I'll just go ahead and put in what that is here, mg times h1. So this to me looks like the entire energy picture here. There's the initial potential energy of the box. When everything's done, it gets spread into potential energy of the spring, plus a little bit more potential energy of the box because it's sitting not quite on the ground. Now lastly, then, we have to reconcile some of these distances here because we have a lot of variables in here. We have this h, the height above the ground, and we have this h1 here. And if I look very carefully, it looks like to me, though, that if you sort of examine the way all these distances come out, they're all sort of interrelated here. So remember that this distance right here is delta S. That's how far down the spring went. That's an h1 right there. And if I look really carefully here, it looks like to me that the total h that the box was at before looks like that's going to be equal to A, the distance the box was just above the spring when it started, plus delta S plus h1. So it looks like to me that this capital H here, this total distance the box was above the ground before the problem started, is equal to A, that's its distance above the spring, plus delta S plus h1. So there's nothing too magical about this, it's just sort of some geometry here. This height here is this distance here, plus this one here. So see, all the parameters are interrelated. Now the variables that I do know in the problem are this variable A here, so I definitely want that floating around in the problem. And the compression length of the spring was probably given as well. So I think probably the best thing to do then is to solve this equation here for h1, or h, it doesn't matter, I'll just leave it the way it is here. And I'll just sort of fill in h here, so h is actually mg times A plus delta S plus h1, something like that. And all that goes into the potential energy of the spring, the 1/2 k delta S squared plus mg times h1. So I just sort of filled in what capital H is here in favor of some of these other variables. So I'll sort of stop the solution there. I think you can finish it from here, but if you look very carefully about what's going to happen, I have an mg times h1 right here, so that's just going to cancel out. That mg h1 is going to cancel out, and that whole term is just going to be gone right there. And what I'll be left with here then is an mg times A and mg times delta S is equal to 1/2 k times delta S squared. So it looks like the problem can be reduced down in terms of the variables I know, because it turns out that A and delta S here were given in the problem. So you can solve for, I believe, it's the spring constant they want. In other words, they want to know how stiff the spring must have been to cause all this to happen.